Hello guys, and welcome back to my YouTube channel on the Vig Structure Hub. This is a place where you learn, build and innovate. Today I want to solve a problem from three-moment theorem, or sometimes you call it the Clapeyron theorem. And before I can begin, I want to encourage you guys to buy such a calculator, or you can buy Casio FX991. So such a calculator will help you in solving simultaneous equation arising from three-moment theorem. At times in your exam, you may find time is very limited. So you have 3 hours, but for that 3 hours, if you don't manage your time very well, you will end up even doing 1.5 question. It is because of time management. And if you buy such a calculator, it will help you in solving three-moment equation when it comes to simultaneous equation, because it will save your time. It will save your time. So what you need to do, you just key in the figures in the calculator, and then it gives you the answers, the unknown, maybe 3 unknown, 4 unknown, like that. And something you should do about this calculator is to know how to use it. So if you don't know how to use it, it may become a problem in your exam. So you should start using it as early as possible before going to an exam. So let's tackle a question for today, and the question is on the board. So for those who have not subscribed to this channel, I do encourage you guys to subscribe and hit that notification bell so that you may be the first person to be notified when I upload a video. So let's go back to the question. So stay tuned from the start up to the end. The question is from three-moment theorem, or sometimes you call it the Clapeyron theorem. And the question reads, sketch the bending moment diagram and shear force diagram of the figure below, showing all critical points. So the question carries 20 marks. As you can see, this is a beam, and the beam is fixed at point A. It has a pinned support at point B, also a pinned support at point C and at point D. So also the beam is loaded with 5 kilonewton per meter, that is IUDL, between point A and B. We have a point load of 50 kilonewton placed at point E, and then we have a combination of a UDL and a point load. So a UDL is 5 kilonewton per meter and a point load of 10 kilonewton at point F. So again, we have 3I, 2I, and I. We have 5 meters, 3 meters, 2 meters, 2 meters, 2 meters. So let's see how we can solve such a question. So the first thing to do, as usual, you have to extend this line so that you may have enough space to draw the required diagram. And then, so solution. Then the next thing to do is to extend an imaginary span where our beam is fixed. So that is point A. So our beam is fixed at point A. So you will assume an imaginary span like that and call it A. So this distance will be LO. Why are we assuming this imaginary span? We are assuming this imaginary span so that it can help us to get fixed moment at point A. So we begin by free span moment. Free span So free span moments. So we'll begin by span AB. So span AB. So span AB, as you can see, it is loaded with a UDL. The formula is W L square over 8. So this one is equal to 5 times 5 square over 8. Then you punch your calculator. So 5 times 5 square over 8. So that is 15.625 kilonewton meter. We proceed to span BC. So as you can see, our BC, it has an eccentric load of 50 kilonewton. So eccentric load, it means it is not at the center of that span. So the formula is W AB over L. So our W is 50 times A is 3 times 2. L is 3 plus 2, that is 5. And you get your answer. So that is 50 times 3 times 2 over 5. So that is 60. Then we proceed to span CD. Span CD. So as you can see, span CD, it has a combination of UDL and a point load. So the formula for UDL is W L square over 8. Then plus, we have an concentric load placed at the center, which is 10 kilonewton. So the formula is WL over 4. So this one is equal to 5 times L, which is 4 square over 8 plus 10 times 4 over 4. Then you punch your calculator. So that is 5 times 4 square over 8 plus 10 times 4 over 4. So that is 20 kilonewton meter. So after calculating our free span moment, what follows next is to draw a free span moment diagram. So let's draw our free span moment diagram. So we'll draw it here. So let's draw our free span moment diagram. So span AB, it has 15.625 kilonewton per meter. Span BC 60 kilonewton meter. Span CD 20 kilonewton meter. So the highest is 60, which is span BC. So span BC is here. So we'll approximate. So let's say this is 60. So we will join. these 2 points, and also here. Make sure your work is very neat. So that is 60. And then we proceed to 20. So 20 is CD. So 20 will be a little bit lower than 60. So something you should note, when it comes to a diagram for a combination of a UDL and a point load, so the moment diagram will always take the parabolic shape. It will bend in a parabolic shape and not like this. So this is what we will have. So that is 20, like that. And then the last one is 15.625. So we approximate 15 a little bit lower than 20. So that is 15.625, like that. So having done so, we will now apply the 3-moment equation. So apply 3-moment equation. So for you to apply 3-moment equation, you need to have 2 consecutive span. So for us to have 2 consecutive span, we'll start from our imaginary span, which is span OA. So we'll have span OA and AB, like that. So after choosing your span, which is span OA and AB, you will write the 3-moment equation. So the 3-moment equation from this span will be MO LO over IO, because MO is the moment at this point, and because it is an imaginary, it will be moment O, and LO over IO plus 2MA into bracket LO over IO plus L1 over I1. So this is L1, this one is L1, like that. So plus MC, MB, not MC, plus MB, L1, I1 is equal to minus 6 into bracket A0 x bar 0 over L0 I0 plus A1 x bar 1 L1 I1. Close the bracket. So this is the equation, the 3-moment equation for span OA AB. So no need to cram this equation. You can just generate it from this span you have chosen. So for O, it will have, we will have MO LO over IO plus we have 2A, 2MA LO over IO plus L1 over I1. You close the bracket plus MB L1 I1. Yes, MB times L1 I1 is equal to minus 6. Then the area of this imaginary span which is A0 x bar 0 over L0 I0 plus the area of this times the centroid of this over L1 times I1. So let's proceed. So I will clear here at the top. So having this equation down on your book, so what you need to do is to come and calculate the areas and their centroid. So we'll start by A0, x bar 0, which is equal to 0, and then we proceed to A1, x bar 1. So A1, x bar 1. So the A1 x bar 1 is the area of this parabola. So the area of parabola is 2 over 3 times base, which is 5, times height, 15.625, times the centroid. The centroid is a half of the base. So the centroid will be 5 over 2. Then you punch your calculator. So 2 over 3 times 5 times 15.625 times 5 over 2. So that is 130. 130.208. 130.208. So that is A1 x bar 1. And then you will come to this equation and insert the known values in the equation. So M0, L0, I0 will be automatically be 0. So no need of repeating ourselves. So we proceed to 2MA. So we have 2MA into bracket 0 plus, because this is 0, plus L1, that is 5 over 3, because we have 3I. And then we close our bracket, plus MB L1 is 5 over 3, that is I1, is equal to minus 6 into bracket, this one again is 0, so no need of repeating ourselves, just put there 0, plus A1 x bar 1 is 130.208 over L1 is 5 times I1 is 3, like that. Then you punch your calculator. So 5 over 3 plus 0 times 2, that is 10 over 3, like that, plus 10 over 3 MA plus 5 over 3 MB is equal to minus 6, open the bracket, 130.208 over 5 times 3. So that is minus 52.083. So call it equation 1. So this is equation 1, like that. So we proceed now to span. The next span is span BC, no, span AB BC. So that is our next span. Again, you will write your formula. So our formula will be MA L1 over I1 plus 2 MB into bracket L1 I1 plus L2 I2 plus MC L2 I2 is equal to -6, open the bracket, A1 x bar 1 over L1 I1 plus A2 x bar 2 over L2 I2, like that. And then after doing that, you will now come and calculate the values for area 1 and x bar 1 and area 2 times x bar 2. So A1 x bar 1 is 2 over 3 times 15.625 times 5 times 5 over 2. So the answer will be 130.208. So after calculating A1 x bar 1, we now proceed to A2 x bar 2. So for A2 x bar 2, we have two methods. So the first method is to calculate the area of the whole of this triangle times its centroid, which is a half times 60 times 5, 3 plus 2, that is 5, and then times the centroid is b plus L over 3. So I will explain. So for you to find B and A, you will consider a common joint, which is B. So the distance which is so close to B is A. So this is A, and the remaining distance is B. So from B to here is A. Then from here to C is B. So that is it. So we'll end up having a half times 60 times 5 times B. B is 2 plus L. L is 5, then over 3. Then you punch your calculator. So that is a half, which is 0.5 times 60 times 5 times 2 plus 5 over 3. So that is 350. Like that. So the second option is to divide this bigger triangle into two triangles, that is triangle number 1 and the triangle number 2. So you will calculate the area of triangle number 1 times its centroid plus area of triangle number 2 times its centroid. So this is how we do it. So we start from number 1. So that one will be a half that one will be a half times base is 2 times height is 60, then times the centroid. The centroid, again, our common joint is our point of reference. So for this case, for this method, we will be moving from this side as we proceed to the common joint. So that is 2 over 3. The centroid is 2 over 3 times 2, then plus the area of the remaining triangle, which is triangle number 2, times its centroid. So we'll end up having a half times 3 times 60 times the centroid. Because we are coming from this point, it will be 2 plus the centroid of this triangle number 2. So that is a third times 3. Then you punch your calculator. So a half, which is 0.5 times 2 times 60 times 2 over 3 times 2. So this is 80 plus here 1, here 1. So 1 times 1 is 1 plus 2, that is 3. So you have 3 times 60 times 3 times 0.5. That is 270. If you add the 2, you will get 350. So the answer is the same. So for you, you have to choose a method that will save your time. So after doing so, we will now insert the known values into the formula so that we may have our second equation. And this is how we do it. So MA, we have MA times L1 over I1. So MA times L1 is 5 over 3 plus 2 MB into bracket 5 over 3 plus L2, 3 plus 2, that is 5 over 2 plus MC, L2 is 5 over 2, like that, is equal to negative 6. A1 x bar 1 is 130.28. So 130.28 over L1 I1, that is 5 times 3, then plus A2 x bar 2, 350 over L2 I2, so that is 3 plus 2, that is 5 times 2, because it's 2I. Then you simplify your expression. So if we simplify, we'll end up having 5 over 3 MA plus, let's open the bracket, 5 over 3 plus 5 over 2 times 2. So that is 25 over 3 MB plus 5 over 2 MC is equal to, open the bracket again, 130.28 over 15 plus 350 over 10 times negative 6. So that is negative 262.112. So this is equation 2. So that is equation number 2. So let's proceed to the last span. So you have span BC, CD. So let's write our 3-moment equation from span BC, CD. So we'll have MB L2 I2 plus 2 MC into bracket L2 I2 plus L3 I3, close the bracket, plus MC L3 I3 is equal to minus 6 open the bracket, A2 x bar 2 L2 I2 plus A3 x bar 3 over L3 I3, like that. After doing so, we'll proceed to calculation of area 2 x bar 2. So area 2 x bar 2 is equal to, again, you want to find the area and the centroid of this triangle, considering our common joint is C. Our common joint is C. So now our A will change. Our A will change. So a common joint is A. So it means, no, our common joint is C. So it means our A is this and our B is this, like that. So we'll end up having a half times 60 times 5 times the centroid. Centroid is B plus L over 3, like that. So let me create space for more calculation. So if you can punch our calculator, we will end up having 150, then B is 3 plus L is 5 over 3. So that is 150 times 3 plus 5 over 3. So that is 400. So let's use the second method. So that second method, it will be the area of 1 and 2. So again, our common joint is C. So for this second method, we are moving from this side to a common joint. So if we start from area of triangle number 1, it will be a half times 60 times 3 times 2 over 3 times 3. plus a half times 2 times 60 times 3 plus 1 over 3 times 2. So let's punch our calculator. 0.5 times 60 times 3 times 2 over 3 times 3. So this is 180 plus so that is 2 over 3 plus 3 times 60 times 2 times 0.5. So this is 220. This is 220. So the answer is 400. The answer remains the same. So choose appropriate method for you that will save your time. Don't use the two methods I'm using. So after calculating a3 x bar 3, which is 400. Now this is a2 x bar 2 equals to 400. Now we proceed to a3 x bar 3, which is equal to, the area of this is 2 over 3 times 20 times 4 times 4 over 2, which is the centroid. 4 over 2 is the centroid. We punch our calculator. 2 over 3 times 20 times 4 times 2. That is 106.667. So that is a 3 x bar 3. Now let's insert the known value into this expression, which is for span BCCD, which is MB L2 I2 plus 2 MC L2 I2 plus L3 I3 plus MD L3 I3 is equal to negative 6 A2 x bar 2 L2 I2 plus A3 x bar 3 L3 I3. So we'll have the known values into this expression. We'll end up having L2 I2, that is 5 over 2 MB plus 2 into bracket 5 over 2 plus L3, 2 plus 2 is 4, 4 over 1 MC plus 4 over 1 MD is equal to negative 6 A2 x bar 2, that is 400, over 3 plus 2, 5 times 2 plus 160.667 over 4 times 1. Then we punch our calculator. So that is 5. So that is 2.5. So this one is 2.5 MB plus 2.5 plus 4 times 2, that is 13 MC plus 4 MD is equal to 400 over 10 plus 160.667 over 4. Times negative 6. That is negative 481.00. So we also know that moment at D, MD is equal to 0. Why? Because it is a pinned support. So our final equation will be 2.5 MB plus 13 MC is equal to negative 481. So this is equation number 3. So we have equation 1, 2, and 3. So you will use a calculator like this one to solve the 3 unknown. So this is our 3 equations from 3-moment theorem. So this was our first equation. So we had 10 over 3 MA plus 5 over 3 MB plus I have introduced 0 MC to make it 3 unknown is equal to negative 52.083. And then the second equation was this one. So it had 3 unknown, no need of introducing 0. The third one, we had 2.5 MB plus 13 MC equals to negative 481. So I have introduced 0 MA to make it 3 unknown. So after doing so, then you'll come to your calculator. As I told you, you need a good calculator like this one. I hope you can see. So you'll proceed to mode, and then you proceed to number 5. Number 5 is equations. So press number 5, and then the first one is 2 unknown, x and y. And then the second one is x, y, and z. So that is 3 unknown. And then the third one is the quadratic, ax squared plus bx plus c. And then the fourth one is cubic. So ours is the second equation. So we go to number 2, and then you feed it the way it is, 10 over 3, that is 10 over 3 equals 5 over 3 equals 0, then negative 52.083, then 5 over 3, 25 over 3 equals, then 5 over 2, then negative 261.112 equals 0 equals 2.5 equals 13 equals, then negative 481. Then you press equals again. You will get your x, which is MA, as 5.47. So that is MA is equal to negative 5.47 kilonewton meter. You press again equal sign to get MB. So MB is equal to negative 20.31 kilonewton. You press equal sign again to get MC. So MC is equal to negative 33.09 kilonewton. So that is our three moments for MA, MB, and MC. So after calculating these values, you will come and draw your bending moment diagram. So you can combine this free span moment diagram with this moment we have just calculated to get your BMD diagram, or you can find the reaction and then you draw the shear force diagram, and then from shear force diagram you will have to draw the bending, you will have to calculate the values for bending moment from shear force diagram. That value will help you to draw BMD. But for your case, let's combine this and this. So at A, we have 5.47. So you'll come and approximate. Let me use another pen. 5.47. So approximate 5.47. And then you come to bending moment at B, that is 20. So around there, so that is 20.31. And then at C, that's 3. So that is 33.09, then 0. Then you will combine this. So we have, this is positive, this is positive, no, this is negative, this is negative, this is positive, negative, then positive, then negative, positive, like that. So that is our bending moment diagram. So we'll proceed and draw the shear force diagram. And before we can draw the shear force diagram, we are supposed to calculate the reaction. So how are we going to calculate the reaction? So this is the way in calculating the reaction. So you can start from here as you proceed to D. So you can split this into 2, also this into 2. So you'll end up having this one. Like that. So here we have a UDL, that is 5 kilonewton per meter. And here we have a point load which is 50 kilonewton, and then here we have a point load and a UDL. So that is 10, and the point load is 5 kilonewton per meter. So that is 5 kilonewton per meter. And then we have the distances. So that is 2 meters, 2 meters, 2 meters, 3 meters, 5 meters. So this is A. So let's call it RA, like that. And this one, RB1, RB2, RC1, RC2, then RD. Again, we have moment here. Also here. Here is 0, 0. At RC is 33.09, RB 20.31, and then at RA is 5.47. So let's now calculate our reaction. So we'll start by summing moment. Summation of moment at RA is equal to 0. So if you sum moment at RA, automatically you are looking for RB. So the distance from here to here is 5, and RB1 is moving in anti-clockwise direction. So we have negative 5 RB1. Then you come to this moment, which is 5.47 in anti-clockwise direction, minus 5.47 times the UDL. It starts from here up to here, so it is moving in clockwise direction, plus 5 times 5 times 5 over 2, because it is acting at the center of the distance. You change it first to a point load by multiplying it with the distance. Then you come to this 20, which is moving in clockwise. So plus 20.31 is equal to 0, which imply RB1 is equal to, then you can carry out the operation and get RB1. So the answer is 15.47 kilonewton. So RA is equal to 5 times 5 minus 15.47. So which imply RA is equal to, so that is 25 minus 15.47. So that is 9.53 kilonewton. So the reason as to why I'm subtracting 15.47 from 5 times 5 is that the summation of upward forces is equal to summation of downward forces. So this is the reason. So RA plus RB1 is the same as RUDL, which is on the top. Yes, so it will be 5 times 5 minus 15.47. We proceed to summation of moment at RB2 is equal to 0. So we are summing moment at RB2, so we'll end up having minus 5 RC1. So this moment is in anti-clockwise direction, minus 20.31. Then we come to 50 plus 50 times 3. We come to 33.09 plus 33.09 is equal to 0. Then we carry out the operation to get RC1. So RC1, which imply RC1 is equal to 32.56 kilonewton. So if you carry out the operation, this is the answer. Then RB2 is equal to 50 minus 32.56. So 50 minus 32.56. So that is 17.44 kilonewton. So the reason we made the same as to this one. So summation of upward forces is equal to summation of downward forces. So it means RB2 plus RC1 is equal to the downward force, which is 50. Then we proceed to RC2. So summation of moment at RC2 is equal to 0. So it means 4 plus 4, 2 plus 2 is 4. 2 plus 2 is 4. So we'll have negative 4 RD minus 33.09, because this force, this moment is moving in anti-clockwise direction, minus, no, plus 10. 10 is moving in clockwise direction, so plus 10 times 2 plus a UDL, which is 5. You change it to point load, multiply by 4, then it acts at the center, times 4 over 2. This is 0, it has no impact, is equal to 0, which imply RD is equal to, again, you carry out the operation to get RD. So RD is 6.73 kilonewton. So RC2 is equal to 10 plus 5 times 4 minus 6.73. The reason remains the same. Summation of upward forces is the same as summation of downward forces. So that is 10 plus 20, 30 minus 6.73. So that is 23.27 kilonewton. Now you can draw our shear force diagram using the reactions. So let's draw our shear force diagram. So we'll begin by RA. So our RA is 9.53. So I will approximate from this point. So above the baseline is positive, below is negative. So I will approximate 9.53. So let's say it's somewhere there. So that is 9.53. So I will take 9.53 minus this UDL minus 5 times 5. So you convert it first to a point load by multiplying the UDL by the distance. So because it is going downward, you take this minus 5 times 5. So you'll get negative 15.47. So you approximate 15.47. So this will be an inclined line or a diagonal line like that. So after getting negative 15.47, so after getting this value, which is 15.47, so don't make a mistake of rubbing your answer or deleting your answers on your calculator. So continue adding and subtracting up to point D. So that is negative 15.47. So, and we know that if we have negative 15.47, we should add reaction at B, so which is RB1 plus RB2. So say plus 15.47 plus 17.44. So you'll get 17.44. Again, you come here and draw 17.44. So that is 17.44. After getting 17.44, you will proceed to the next loading, which is 50. So this one will be a constant up to that point. Again, you will take your answer, which is 17.44 minus 50. You will get negative 32.56. Again, 32.56, like that. So it will be constant up to reaction at C. So reaction at C, you will add negative 32.56 by, you will add to RC2 and RC1. So plus 32.56 plus 23.27. So you get 23.27. Again, you approximate 23.27. So this is 23.27. So for this, you will come and minus. So 23.27 minus this UDL from here to here. So that is 5 times 2. You get 13.27. So you'll come here and say 13.27. So this is an inclined line like that. And then minus 10. You will get positive 3.27. So it will come up to there. So 3.27. So 3.27 again minus a UDL, which is 5 times 2, that is 10. That is negative 6.73. So from here to this point and then to the last point, like that. So this is minus This plus, minus, plus, minus, plus. And then you shade your respective areas for visibility. So that is shear force diagram. Again, you can come up with bending moment values from this shear force diagram, which can enable you to draw the bending moment diagram. So if you don't want to use this method, you can use this method. So again, from this shear force diagram, you can calculate the maximum bending moment, and the maximum bending moment, it occurs where the shear force changes sign from positive to negative, and the shear force value at that point is 0. For example, at this point, it is changing from positive to negative, and the shear force is 0. So you can calculate the maximum bending moment. So I leave it at that point. Maybe in your free time, you can calculate the maximum bending moment for this beam. So we meet again in my next session.